Hi everyone. So as was discussed today in our video conference session, this video is just tidying up the last few odds and ends from the lipids subtopic. So let's get going. So what we are missing is this discussion about energy here. We haven't talked about phospholipids. We haven't talked about hydrolysis in alkaline and acidic structure, alkaline and acidic conditions. We haven't talked about cell membranes, but that will fit with phospholipids. We haven't talked about energy storage, thermal and electrical insulation. We haven't talked about, well, we have a little bit, but melting points of fats and oils. And we haven't compared carbohydrates and lipids in terms of their energy storage and density. Okay, so let's get started. So fats and energy is the first we're going to look at. And in terms of these points, we're going to look at how reduced they are, fats versus carbs. And we're going to talk about fats versus carbs in terms of energy storage and density. That's it. Yes. So this is a snippy from the OneNote. So oxidation number of carbon in glucose. So it is it is 6 carbons plus 12 times plus 1 plus 6 times negative 2 equals 0 overall. So 12 times hydrogen is a plus 1. So 6 carbons plus 12 minus 12 equals 0. So 6 carbons equals 0. So carbon is equal to 0. So that's in glucose. When we look at butyric acid, that is C4H3578. C4H8O2, so 4 carbons plus 8 times plus 1. That looks like an H, but it is a plus 1 plus 2 times neg 2 is all equal to 0. So this is 8, this is 4. I have done that right, yeah. So this is 4C plus 4 equals 0. So C is equal to neg 1. So that's, yes. So overall, my oxidation number for my, let me laser point. In a carbohydrate, for example, in glucose, my oxidation number for my carbon ends up being 0, whereas my oxidation number for my carbons in a fatty acid, and this is a very short fatty acid, it's equal to negative 1. This is more reduced because it's gained those negative charges, which means that I can basically fit more oxygen molecules onto this when I burn it. There are more chemical bonds for me to be adding oxygens onto in here, which means that this is going to release more energy. This is what we mean by more reduced. Okay, continuing on. Okay, so what I've got here is a graph of different sources of foods and their energy content. So fats, as we can see, have the highest energy densities. So energy densities, imagine if I basically took a gram each of alcohol, proteins, fats, and carbs and actually burnt them and measured using calorimetry the energy released. The reason we're measuring in grams is because these are mixed substances. So the calorimetry, if I were doing like a pure amino acid, so pure glycine and pure asparagine would have different delta H's. So when we're looking at stuff that is mixed, so a fat is the glycerol and it's the fatty acid. So different fats would have different energy contents, but because these are mixed substances, they're not pure, we measure using energy densities. So fats have by far the highest energy content. Alcohol doesn't do too badly on this scale. Fats have, depending on the type of fat, between about 35 and 37 kilojoules per gram, whereas something like proteins and carbs, they're down at sort of the 15 to 17 range. You do not need to know exact numbers for this. You just need to know that fats are by far the highest energy density of the main foodstuffs we eat. Because you are doing a high school exam, they probably won't ask you about alcohol, but they will expect you to have this idea that fats have the highest energy density, the others are lower. So in terms of our energy sources and solubility, so earlier we talked about glucose. Now, we will discuss carbohydrates in more detail later on, but we've got basically glucose versus a triglyceride. So when you look at the glucose molecule, it is basically that hexagon, and basically all over the shop it's got, and I know this isn't the structure, so don't at me, basically a glucose molecule has all over it hydroxyl groups. It is very soluble. Whereas a triglyceride is like that E-shaped thing, carbon, oxygen. Sorry, I haven't done that right. So it's oxygen, carbon, oxygen, zigzag. Oxygen, carbon, oxygen, zigzag. And I'm doing saturated just because I can't be bothered. Zigzag. And those aren't really very zigzaggy. This is, sorry, in water. This is virtually completely insoluble. So in terms of energy storage, if you want something that you can literally put away for winter, fat storages are really useful for that because they pack a lot of energy into the size of this molecule, as we saw on the previous page. But in terms of actually getting that energy out to the cells, getting it circulating in the bloodstream, glucose is a much more efficient way of doing it, partially because our mitochondria are set up to convert this into ATP using all that Krebs stuff that the bio people have just triggered. So in terms of energy sources and solubility, fats are super good for energy storage, like long-term energy storage. Our carbs are super useful for short-term energy storage and also transport. So it's hard to transport this in the body unless you want to get to the HDL, LDL stuff that we were talking about before. But with glucose, we can transport it comparatively easily because it is so soluble in water. Okay, moving on. Phospholipids. Now, bio people, you will probably be pretty comfortable with these. So let's get straight into it. So phospholipids are triglyceride derivatives and they are components of cell membranes. So basically all you need to know for phospholipids is that, okay, so for phospholipids, bio people, this is likely to be so far so recap. So we have a polar end, which is this guy here. So that's the same structure as is just these blue dots that we have here. So that is hydrophilic, it loves water, and it is polar. We then have over here a section that is hydrophobic, which are these bits, these leggy bits that we've got here, and these leggy bits we've got here. So this is what is called a phospholipid bilayer. It's a bilayer because there's two sides of it. So what do you need to know for the exam? You need to know that this, and therefore this entire molecule, is derived from a triglyceride. Derivative. And you need to know that they make up cell membranes. You need to know this general structure of a hydrophilic head. And then hydrophobic tails. Okay, that is a nutshell on phospholipids. Let's move on. So lipids can be used for insulation, and I'm going to be talking about two different types of insulation. We've got thermal and we've got electrical. Now, because you basically only need to know that lipids can do this, I'm not going to go into a massive amount of detail. I'm just going to give you a couple of examples. So let's look at what this looks like in the study guide. Lipids act as thermal and electrical insulation. Okay, let's talk about Schwann cells and blubber. So let's go back to our pen. So Schwann cells, when we look at a neuron, we've got a big long axon before we get down to the synapse down that end. So we've got our dendrites, 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 dendrites. So we've got this big long thing which is called an axon. Now those axons in humans can easily be over a metre long. The longest nerve that we have in our bodies is a sensory neuron that goes from, and this has been a while since I've read this fact, so if somebody's got more up-to-date information, that's awesome. But for example, we have a sensory neuron that detects touch in the tip of our big toe, and its axon goes all the way up our leg into our spinal cord. Now, if I were running, all nervous signaling is electrical. So if I had just like in my lounge room, a wire that was going from like the PowerPoint to the back of my TV, or like a data cable, I would want that to be insulated. The same thing goes with the electrical wires in our body, which are our nerve cells. So Schwann cells are a type of cell that wrap around our axons, and they act as electrical insulation around our axons. You do not need to know how they work, you just need to know that they exist. So these cells here are for electrical insulation of neurons. So in multiple sclerosis, what happens is in the brain, these cells deteriorate, which means that you get effectively cross wires and the message doesn't get transmitted from my dendrites into my soma down my axons smoothly, which explains a lot of the side effects that we see in people with MS. Oh, sorry, be good if I could. Yeah, so that is our electrical insulation. Now, in terms of thermal insulation, there was this Instagram account or Twitter account, I can't remember which, but it was of one of the parks services in either America or Canada, and they had photos of bears in like at the end of winter versus the start of winter. So bears hibernate, and before they go into hibernation, they eat a whole bunch of stuff, and they basically store a lot of that as fat for the reasons we discussed earlier. And then over the course of winter, while they're hibernating, they consume those fat molecules. So whales and bears, it is a thick layer of what is called subcutaneous fat. So subcutaneous is under the skin. So a thick layer of fat under the skin that acts as insulation. So a lot of marine mammals have this, so whales and seals and things like that. So whale blubber used to be used as an oil for lanterns and things like that. It's one of the reasons why whales were hunted, because they did have such large stores of fat. So that is subcutaneous fat, and this is thermal insulation. So when you see somebody who's about to swim the English Channel or something like that, they will often cover themselves in fat, and that's because it does add that insulating layer. Okay. So the melting points of lipids, we have discussed this briefly, but just worth talking. I thought it was worth talking about again. So prediction of the relative melting points from their structures. You do not need to know exact numbers. You just need to say, given these two fats, given these two oils, what would their relative melting points and boiling points be? Sorry, melting points. What would their relative ones be? And that. Okay, so what I've got here are the exact same images that I put in the OneNote a week or so back now. Up here we have a saturated fatty acid and an unsaturated fatty acid. Now, why that's important when we're looking at fats, for example, we've got our glycerol, which is kind of this E shape. If I've got 3 saturated fats, Remember, those carbon chains are straight-ish, which means that I've got increased packing. The molecules are going to be closer together, which means I'm going to have increased LDF. So those non-polar, etc., forces of attraction, those instantaneous dipoles. So the longer the fatty acid chain, the higher the melting point is going to be. But generally speaking, you'll be comparing a saturated versus an unsaturated. So think about the packing, which leads to a difference in LDF, which leads to an increase in melting point. So basically, if you've got a fat versus an oil, fats tend to be solid at room temperature. Oils tend to be liquids at room temperature. And basically, it's the difference between saturated and unsaturated fats there. So they will only be asking you to talk about it in comparison. They won't ask you for an exact number. They're after what is the qualitative difference between saturated and unsaturated fats in terms of melting points. Okay, moving on. So acidic and alkaline hydrolysis of fats. It is really a tiny little fraction of this thing here. I've talked about it using enzymes. Let's now quickly talk about it in the context of alkaline and acidic conditions. So soap making is, so in the chemical term for it is called saponification. Now, literally half of you study French. So sapon comes from the French term savon, which is soap. Ification means making. So saponification is soap making. So this is our alkaline. So there is an awesome segment in Fight Club where the main character is stealing fat and then reacts it with a base in order to make the sodium salts of our fatty acids. And generally they'd be unsaturated. Most soaps are vegetable soaps. So this thing here, by turning it into an ionic compound, it's actually a bit more soluble in water. And it's water soluble because of this ionic portion here, not that ionic portion here, this ionic slash charged portion here. Then you've got this big long non-polar section, which means that this one end can dissolve in fats and the other end can attach to water molecules. This is how soap works to get grease off your hands. So the non-polar portion of the soap molecule, this non-polar portion dissolves in the grease that's on your skin, and then we use the attraction between this polar end and the water molecules that you're using to wash your hands with to actually pull the fat off your skin, which is why your hands feel dry if you've used too much soap, because you're pulling off not just any added oils, you're pulling off the oils that are naturally produced by the skin. So that's soap making, which is the alkaline hydrolysis of fats. Now, can also do this with acidic. Basically, it's the idea that they want you to have is that acidic or alkaline is no catalyst. Sorry, no enzyme. Remember we talked about denaturation back when we were talking about proteins and enzymes. If I were going to have a very strong alkaline or very strong acidic solution in order to break down these fats, I wouldn't be able to use enzymes because remember they would denature. So acidic hydrolysis looks pretty much exactly like normal hydrolysis. There aren't really any specific features to that chemical reaction you need to be aware of. So let's continue. So let's do a last check of the study guide. Okay, so in yellow, I'm going to highlight the stuff that we talked about today, and then hopefully double check it for yourself when you watch this video. That should bring us to the end of lipids. So fats, oh, I need a highlighter, not a pen. Fats are more reduced than carbohydrates, so yield more energy when oxidized. We then talked about phospholipids being derivatives of triglycerides. We talked about alkaline and acidic conditions. We talked about cell membranes, energy storage, and thermal and electrical insulation. We looked at the melting points of fats and oils, and we talked about carbs versus lipids in terms of energy density and solubility. Thank you so much. That brings us to the end of lipids, and have a fantastic rest of your day. Bye.